that so this huge dust and gas cloud had a little amount of rotation, angular momentum, and because these particles are like a collection of small particles, right, gas and dust, as they rotate, these particles actually were forced towards the axis of rotation, and it eventually over the years turned into a disk of matter, gas and dust. We call it accretion disk. Okay. And you can see a lot of disks out there in the universe. If you have a very powerful telescope, you point that telescope into any direction, and if you can see up to infinity, you can see this disk kind of things. Call them galaxies. Okay, disks, very common. So therefore, you see, this rotation is a very common thing. The disks of gas and dust clouds, and then even bigger structures like galaxies, are formed because of an angular momentum. Okay, so what really happens is that as it rotates, it accreted or collected heavy stuff to the center. Okay, it collects everything into the center, but particularly the heavy stuff. Uh, and then because of this concentration of matter at the center, and it's a flattened disk, it is initially maybe it was a three-dimensional structure, irregular structure, but it was taking shape gradually as it rotates on a plane parallel to the axis. It flattened, so now it's a flat long disk kind of thing, and at the center matter was so concentrated, so close to each other, they were flying very fast, colliding each other, giving rise to the temperature. And at some point of time, this temperature was enough to fuse hydrogen into helium. Okay, so at that point, um, that's the beginning of a sun, right? Star. So that is how our sun was born. Initial stage we call is a protostar, right? Not a perfectly shaped up star, but something which is going in that direction. So when the sun was born, right, um, we will look at the stellar evolution at a later time. Stellar evolution means how a star is born, how it lives its life, and how it ends its life, right? Stellar evolution. It's a complicated thing, but now scientists have almost tracked it down, the whole process. There are a lot of different types of stars, right? A whole bunch of stars at different colors, sizes, etc. Most of these stars have already been tackled down, right? Supergiants, dwarfs, etc. Right? One common thing that most of the stars demonstrate at the early stage is that they have what is called T-Tauri wind. It's a wind of subatomic particles and radiation coming out of the sun, early sun, right? And this wind has a momentum. That's why it's called wind. It's not just radiation. Radiation also has a radiation pressure. Okay. Light has a pressure. When the light falls on you, you push back a little bit, right? Say somebody flash a light on you, you actually push back a little bit. If you can measure that using very high sensitive equipment, you can figure that out, right? It's negligible, but in absolute terms, it is not zero. So this radiation pressure swept all the remaining matter from the near surrounding of the sun. This is the sun here. This area was cleaned up. It's like a vacuum cleaning of the inner part of the solar system, right? Or maybe dry cleaning, not vacuum cleaning. There was a wind, dry cleaning, right? You clean your clothes using air, right? Something similar to that. So all the dust particles in here were actually swept away. So as you go farther away from the sun, this radiation pressure is not that great, and at some point of time, literally there's no radiation pressure, so that all the gases and dust were actually accumulated at far distances, maybe somewhere over here, okay, not in the uh, inner areas. So what was left around the sun was like heavy stuff, heavy elements that were able to withstand the radiation pressure of the sun, of the T-Tauri wind, like heavy metals, carbon, iron, magnesium, stuff like that. Okay. Uh, and these particles, heavy stuff, were rotating around the sun, and they were colliding each other, making bigger and bigger chunks of matter, starting with few grams maybe to kilograms to tens of hundreds of kilograms, like that. Okay. And they were attached to each other as they move around. Everything was like going around the center. Actually, they form the planets: Mercury, Venus, Earth, and Mars. Okay. The other thing is that you need to remember when there's a big mass in space, it doesn't allow other masses to grow around it. Right? In human society also we can see that if there's a powerful person in certain area, he doesn't like other people to be powerful, right? You know that. He wants other people to be like followers. Okay. You have seen this many a time, in particularly in societies like Sri Lanka. Uh, so these planets, even though they are small, right? Mercury, Venus, Earth, and Mars, all the matter around it, they actually accreted to themselves. All the particles around Earth got them accreted into the Earth itself. Mercury, all the particles around Mercury got them accreted, attached, like glued to Mercury to become bigger and become bigger. So that is how even people create their dynasties. Okay, they get more and more people around them, right? Uh, by hook or by crook. Okay, doing all kinds of things, right? So we can see physically it is happening in the universal scale also. All the matter actually, they had to make a choice, right? If you a particle over here, you had a choice, which is the closest one to me, Mercury. Then I go to Mercury and be part of Mercury. Or if it is Venus, I go to Venus and be part of Venus. Like that, all the other matter particles, they went to nearby um, uh, planets. Okay. And then you created these planets. And because there was no the matter was limited in this area, these planets were able to grow up to a certain mass. They were not able to grow beyond that. And if you ask me, right, let's say we started off in this area with 1 million particles, right? Million is a very small number in this context, but to make it life easy for us to understand what was happening at that time, let's say there was 1 million particles, right, around here. Now we have Mercury, Venus, Earth, and Mars, 4 objects. So the million particles went into form just 4 planets: Mercury, Venus, Earth, and Mars. And if it was the case, what was it just before that, in between? Maybe there was a time there were not 4 planets, maybe 100 objects, 200 objects, and even before that, maybe 1,000 objects. Now you can see what's happening, right? Starting with 1 million particles, it becomes like 10,000, 1,000, 100, 10, 5, 4, like that. Okay. Now, if you ask me going forward in another few million years from now, what will happen? Now we have four objects. Let's forget about the names and all. Just four objects in an abstract way. Can these four objects become like two objects? So this is what I'm saying. I want you to think like that. We just can't say, no, it's not going to happen. Because that's not a very rational answer, right? Maybe we don't like it, and that's why we say, no, that's not going to happen. In our normal life also, sometimes we talk like that, no? You have recollection of what your own experience. Sometimes you say, no, I don't think that will happen. But if you just take a step back and think, could this really happen? Then sometimes you might see there's a possibility, right? So I want you to be people like that. Do not just take values from the face value, right? You sit in the right in the middle, look at the observation, look at the data, no bias at all, right? And then you decide what's likely, whether you like it or not. Whether it has not happened before, doesn't matter. There are things happening for the first time in the world, right? In your life also, you will see the first thing in your life. You have to go through these experiences. One of the problems with the intelligent people, those who know physics, mathematics more than the other people, they always try to extrapolate, take the experience, going from past to the future, crossing the present. That's what we do most of the time. And sometimes when you do this over and over and over again, sometimes you get locked in that process, which means you can only think anything that has happened in the past, even without knowing that there are things that can happen for the first time in the world, right? You completely shut that door and you always think of your past experience and near present and then predict your future. So this is good, but this is not completely correct. Therefore, you should be open for the first time things that the world has never seen before. Don't say no to that kind of thing just because you haven't seen it before. Okay. Right. So if you ask me, or if you think to yourself, can these four objects become two in the future? Is a very legitimate question. You think yourself. I'm not going to tell you anything because that's not the purpose of this course. I want you to think about it. Right? If it is coming from the past, right, starting with a million particles, now four objects, and in between, it didn't happen on a particular day, These million particles did not turn into four objects overnight at some point in the past, right? It was an evolution. So therefore, have you done with the evolution? I don't know. It looks like it's almost settled, right? So therefore, there's no further modification to this one going forward. We would like to think like that because that is human nature. We don't want to deal with things that are still changing. You want to finish your exams, you want to finish this and that. Until you finish a certain thing, you are frustrated, you're not settled, you can't sleep because that's working in your back of your mind, right? But I want you to be able to deal with those situations, things that are work in progress. Okay, we don't want to rush things to finish it up. That's the very nature of the world. We don't know, but it looks like the dynamics have settled already, and going forward, unless there's a serious disturbance, right, this will continue for a very, very long time without major change in the structure. Right. So, what is there over the other areas farther away, right, from the earth, from the sun rather. Now the story continues. The light matter, which is gas and light dust, etc., was swept into the outer regions of the solar system, these areas, and these particles also underwent the same process. They were colliding, they were attaching to each other, making small planetesimals, and then glued them together to make big ones. Basically, this is gas, not the heavy matter, right? But there were a lot of gas because it was a gas cloud anyway, right? A lot of gas with little amount of heavy stuff, and most of the heavy stuff is now here, and 99% of the matter, which is gas, is over here, and they were accreted to bigger planets because there were a lot of matter. And when you accrete this matter, because it's so much matter there, the planets that were formed there were big, right? What are they? Jupiter, Saturn, Uranus, Neptune. And if you want to talk about Pluto, that's a separate story. It's better not to talk about Pluto right now. Just look at few Jupiter, Saturn, Uranus, and Neptune. They're all very big planets. Now, this hypothesis clearly explained the observation on a scientific footing, right? That's why this theory is so widely accepted now, the hypothesis rather, right? This question was there a long time ago. Why the inner planets, why there's a structure, inner and outer, in the first place? And why inner planets are rocky, heavy planets, whereas the outer ones, which are big but very light, I mean low density, right? Like Jupiter, Uranus, Saturn, and Neptune. So if this was not scientifically explained, this hypothesis could have had a hard time, right, getting accepted in a wide scientific community, because any single observation, right, which is not reasonably described again on a scientific basis by the hypothesis itself, is a killer blow to the hypothesis. That's how the science works, right? So maybe for some time it was like a question mark whether we can continue with the nebula hypothesis or not, because this apparent dramatic difference between inner solar system and outer solar system needed an explanation, and there was none for some time until that particular observation. What was that? The T-Tauri wind coming out of very early stars, protostars, right? So that differentiation had to happen at the early stage, not at a later stage, right? If there was no T-Tauri wind, right, during in the stellar evolution, right, from the birth to the end of the star, if there was no such thing like T-Tauri wind, particularly at the early stage, this theory could have not been properly explained, particularly this separation. So the moment scientists discovered the T-Tauri wind, it actually reflected on the nebula hypothesis the following day. Then the people were talking about, oh, this is the case. This is why the solar system is actually phased out into two segments, inner and outer, and why the inner parts are like solid heavy metals and the outer part is basically gas giants. So it was a perfect match. Okay, it was a perfect match. On one hand, the scientist was able to describe the stellar evolution process, and at the same time, they fill a gap in the Nebulae hypothesis. Right. So I just want you to look at the screen and read for yourself. Everything I explained is actually written over here. Take a minute or two, carefully read it. All right. Any questions up to now? We have to work this out step by step. Right? I don't want to rush. I don't want to complete any syllabus or any target tutorials. No, this is a different course. You know that. So please ask anything that you want to get clarified further. So you can write on the chat. Right. So then the separation between the inner and outer solar system is in that area we give the name frost line, and beyond that is the outer solar system. And you can see these numbers. About 99% of the mass of the planetary nebula is like gases, and the planets that were formed beyond the frost line were too big: Jupiter, Saturn, Uranus, and Neptune. So I'm not talking about Pluto. So the Jupiter is like 5 astronomical units away. You know what this means, right? AU, astronomical unit. That is about 150 million kilometers average distance from the Earth to the Sun. And if you go 5 times, right, that area, a lot of gas and dust were created together to form Jupiter. And then Saturn, it was a bit late to form. Therefore, by the time it started accreting matter, most of the matter had already been accumulated or accreted by Jupiter. So whatever left over accumulated by Saturn, spatially separated. So Saturn was what it was at in that area, okay, eventually form into the planet. So all these things, the evolution, how matter get created into forming planets and all, were simulated in computers, physics-based computers, right? And they have already proven it beyond beyond the state of a hypothesis. Okay, you know, the astrophysicists who do these kind of simulations is, you know, you have heard of multi-body physics, right? Multi-body physics. Let's say you have 10 particles, right, in a three-dimensional space, x, y, z. Every particle has x, y, z position. Let's say there is no gravity, because here on Earth we have gravity, but if you think about the space, there's no gravity. Let's say some isolated uh, area in the space, not on a planet, so there's no gravity field, and you have 10 particles. You have 10 particles. Okay, so these particles are um, you can give them XYZ position. So the first thing you do is XYZ position, and then you give them some velocities also. You can give little velocities, arbitrary velocities, right? Uh, and you can simulate, write down the dynamic equations for each and every particle. Okay, each and every particle. So I can draw it over here for you to understand what I really try to explain. Let's say these are the particles, 1, 2, 3, like that. So it's a three-dimensional structure, right? There's no gravity. So you create this model in a computer, right? How many particles, right? So they you can give them masses. Let's say this is M1, right, like that, and this is M10 or whatever, right? And also your positions XYZ you specify. And if you want, you can give a little velocity also. Let's say V1 here, and give another velocity. Right? Velocities, you can assign velocities. If you look at one single particle over here, the same one, it has a velocity in that direction. After delta t time, after very small time, its position is going to change. Not because of this velocity alone, but because of the acceleration by the other particles on this particular particle. M1 is attracted by all the other particles, right? You can write the gravitational pull by the other particles on M1. So there is a resultant force on M1, and there's an acceleration towards that direction. But altogether, there's already a velocity in this direction. So you can write down the equations and simulate the motion of this particle M1. But it's not only M1, all the other particles are also moving. So now you have to do the parallel computation. Things become very difficult now, right? If you think about 10 particles, you need to have 10 parallel threads, each thread for one particle. And when it happens, it has to look at all the other positions, right? And then work this out. Or if you want to do this in one single thread, normal computer that we use, you have to freeze all the other particles and move this one and bring that one back to the original position, move the other one, keeping all the other particles in their respective places. Like that, you have to do this for all 10 and then update the positions. That's how we normally do. But that is not very close to the reality. So what you are trying to do here is that this is what physicists do using very high speed, high capacity computers. They try to model multi-body dynamics, okay, to figure out what's going to happen to a very huge gas and dust cloud. And they have actually done this. Million particles, 10 million particles, like that, right? To see for themselves what it was like back then. And they have figured out the process of forming planets, right? So that's the science behind this hypothesis. Now let's look at the outer part of the solar system. No wonder for you, right? Now, Saturn, Jupiter, Uranus, and Neptune, the big planets, mostly hydrogen and a splash of helium. Because of that gaseous nature, their densities are low. You may have heard or read in books that if you are able to bring Saturn and put it on water, it will float because it is uh, lighter than water. I mean, density is less than water density. Okay. And they show rapid rotations and they have deep atmospheres. Deep atmospheres. The point is, now here on Earth, you can actually fly on a airplane and then jump out of the airplane with a parachute, and you will float gently down to the surface of the Earth. Then you can uh, touch down, you can step on the surface. There's a clear difference between the air and the ground. Okay, not so in these planets. It's difficult to find where the boundaries, where the solid ground is. At some point of time, it is denser than the ground here, but where it happens is not very clear. Okay, it's a gas ball and it starts getting concentrated, but there's no particular point. Uh, Up to that point, it's atmosphere, and after that is ground. There's no such thing. So if you just try to put your um, foot on the planet, I don't know what's going to happen. You will probably drown. Okay, yeah. So that's what we think. Uh, what would happen if you try to stand on the planet, right? These gas giants, and they have rings and they have lots of satellites. So there's no wonder again. Rings means matter around these planets. A lot of matter goes there. They form into various forms: rings, asteroids, satellites, etc. Okay, so again, very clear, logical fitting of the observation into the theory. Uranus and Neptune were too big and too quick to be accreted at their distances from the sun. Now we have a problem. Even though the story is superficially very logical, if you stop by and dig deep down into any particular point, you will see there are anomalies. So all this long, the story was fine: Uranus, Neptune, Saturn, and Jupiter. But now, according to that multi-body physics, right? This kind of simulations, the simulations sometimes tell certain things to the scientists that they had not thought behind, right, before that. So one of these things is they were too big and too quick to be accreted at their distances. So therefore, what they think is that is believed to have formed closer, right, like between Jupiter and Saturn, and then moved outward. Then moved outward. So that's what we believe. So essentially, what we think is that according to the computer models, the models predict that if we continue Jupiter first, then Saturn, then Uranus, Neptune, there's a problem, because then Uranus, Neptune couldn't have been formed this big. That's essentially what they say. If you go like that, as we would like to believe, right? Jupiter forms, Saturn forms, Uranus and Neptune. That's what people like, right? Because easy to remember and understand, right? But the world doesn't work like that. Uh, Probably Neptune and Uranus were formed in the interim, in the area between Saturn and Uranus. This is just a logical thinking, not a proof again. And then because of these perturbations, we are going to talk about in a while, it was not stable for them in that region, right? Being closer to a big giant is not healthy, because you are not, your surrounding is not very peaceful when you are too close to a big guy. Okay, anything can happen any moment. So now it is between two big guys, Jupiter and Saturn, even more difficult. You don't know what's going to happen next moment. Maybe these two planets, Uranus and Neptune, they formed in between. That's why they are too big, right? Uh, were gravitationally um, pulled out of that position to some other place. Again, you can see the drama we see here in Sri Lanka in the political arena, right? Those who are very close to the big guys, when there's some disturbance, right, they were thrown out, right? They are nowhere now, right? Overnight it happens. So a lot of similarities here in the universal arena, and how the physics works in multi-body physics, right? And what happens in the political and social systems. I sometimes amazed to think like that. This to share with you my experience is this out of the context here. When I teach control systems, right? This is another area that I teach. I see a lot of similarity in the dynamics in the society, how the people think, how the doctors work, and there's very clear analogy between the society dynamics and the control systems. Okay, so therefore I can connect all these things. Whatever I know, I learn about the control systems, I can take it to the society very easily, right? Uh, and at some point, I was thinking about the doctors, how a doctor treats a patient, right? In control systems, we have what's called PID control. I think the doctor is a PID controller for the patient. If you look at how the doctor treats the patient, how he figures out the diagnosis and prescription and all that, is entirely a PID controller. How a PID controller is trying to stabilize a plant. Doctor is trying to stabilize a patient. There's a very clear analogy. Here also, when I see the space, how the planets move, how the solar system was formed, and then when we see how the politics work in the society, my God, there's a very clear analogy, right? Similarity between these two. So sometimes I amaze, I really enjoy just to know that these systems have similar parallels, okay? Very similar parallels. So therefore, I also think it could have been the reason that Saturn and Uranus and Neptune were formed in between uh, the two big guys, Jupiter and Saturn, but they were not able to be there for long because of the gravitational perturbations. At some point in time, they were pulled out of that position and eventually settle at a remote place which is peaceful and stable for these two planets. There may have been other planets other than Uranus and Neptune, and they were also taken out of that position in between Jupiter and Saturn, and they were thrown out to farther distances, completely away, out of the solar system, and we don't know where they are now. And luckily for these two guys, even though they were thrown out of the position, they were able to find a stable orbit beyond Saturn. Therefore, they continue to stay with the family. So it's very, very interesting dynamics. Okay, if you look at how these multi-body systems work. So after about 3 to 10 million years, almost all gas had been swept into interstellar space because the radiation pressure from the sun, it's not only the Titory wind at the early stage of the sun. Um, as long as it shines out, the light comes out of the sun, comes with the radiation pressure, and the matter in the solar system are actually constantly being uh, pushed out of the solar system into the interstellar space. Okay, so over millions and millions of years, now the area has become like clean and empty. So therefore, there's no further possibility for any other planet to form. So now, if you look at, if you observe um, the area between Mars and Jupiter, uh, that area is too big, and it's not completely empty. If you look at that, there are small particles in that area between Jupiter and Mars. So we give it a name, asteroid belt. Okay. Now there was a theory until somewhat recently, and the theory was that there was a planet between Jupiter and Mars, or Mars and Jupiter, going from the Sun outward, Mars and Jupiter. In between these two, there was a planet. And again, because of the very same reason, it's hard to survive closer to a big planet. You have to be big as well if you want to stay, survive, right, near a big planet. So the small planet between Jupiter and Mars was actually broken into pieces, and therefore now we have the debris of that planet. So there was this, again, I don't want to call it a hypothesis, just an idea, just a rational idea. Okay, anybody would have thought it was the case, okay, without any rational or any formal presentation. Okay, there was another reason for that, that is, number sequences, right? Number sequences, like if you start with 1 and the next one 2, and the next one 2 plus 1 3, and the next one 3 plus 2 5, the next one 5 plus 3 8, like that you can create number sequences, right? Somebody has done this number sequence and then compared the positions from the sun to the planets. I don't remember the name, Fibonacci series or something, right? According to that number series, you can find a somewhat close correspondence between the planetary positions and the numbers of the series. Right, the first number is like Mercury, second number is like Venus, third number is like Mars, etc. Earth, and then fourth one is Mars. The fifth one is not Jupiter. The sixth one is Jupiter. Okay, so the fourth number corresponds to Mars. and the sixth number corresponds to Jupiter, and then continues. This is not a very close one-to-one match, but somewhat. And then people thought, oh, according to this number sequence, there's a missing planet at number 5. Number 5, right, whatever it is, doesn't have the corresponding planet. And it it falls in between Jupiter and Mars. And they thought, oh, there was a planet at some point and it was broken into pieces by the gravity of the big Jupiter. So it was very logical, and a lot of people would have wanted it to be the case. But unfortunately, when we build a lot of big telescopes, you could have actually captured the images of these asteroids in that area, and eventually we figured out when you do the quantitative analysis, you take each and every asteroid in between Jupiter and Mars, you tabulate them, you measure the masses and all that, and combine together, and it eventually turns out to be a very small mass. It is nowhere near to the mass of a planet, right? Very small mass, all of the asteroids together. So therefore, now we believe, no, there was no planet in that position, and there is no such relationship between the number sequence and the planetary positions. It's just a coincidence why some of these numbers correspond to the physical planets, right? It's just a correspondence, right? There's nothing beyond that, and there was no planet. Just the elements, the small pieces that were not able to accrete yet, right? Either to the Mars or to the Jupiter. There's nothing more than that. These fancy stories are actually not necessary here. So I think there's something that you have to take away from that point, right? Be realistic, right? Just because you see a number sequence and there's another physical entity and there's a correspondence, your curiosity will drive you. Sometimes it drives you too much. It's good to go to some extent, and then when you get, then after that you have to revert to the rational experimentation, collecting evidence, count them, quantify them, and at some point of time you have to go out of the concept to quantitative analysis, measurements, okay, and then you come to a conclusion with the quantities, not just concepts. Okay, at some point of time you have to convert your concept into a quantity before you take decisions. It is very, very dangerous to take decisions based on just concepts. This is something bad people are doing. You use the concepts and take decisions. So where is the quantitative analysis? It's missing, because quantitative analysis is somewhat difficult to do. It takes time, it needs equipment, and sometimes you have no patience to wait that long to take the decision. You want the decision now. So based on, because it's easy, you have the concepts, what you think, the rational thinking, and then the following day you have the decision. And then you figure out, you learn it by the hard way, the decision is wrong. Because your concept, you have not quantified it. Once you quantify it, then only you will see how big or how small of a number it is. Classical example, the asteroid belt story. Right? There was a number sequence, there were planets, and there was a missing position. And everybody says, oh, there was a planet and it was broken, and now we have pieces. File closed. Everybody is happy. Everybody is happy on a lie. on a lie. It's a lie. But everybody is happy, and there's a very rational uh, explanation. Now, haven't you seen something very similar here in Sri Lanka recent times? Very logical, rational thinking, and the decisions made, and then figure out what a blunder we did. Can some of you guys speak out some of your recent experiences? Rational thinking, decision made, implemented, figured out, it's a total blunder. A lot of things about energy, about fertilizer, about whatever, about even COVID. And the professionals who were there, not only politicians, they do this all the time. There's no surprise. But there are educated people around them, some priests, some doctors, some engineers, some professors even, went on the rational thinking and press on the organic fertilizer revolution, the solar energy revolution, even without any quantitative analysis. Now, if you look at the fertilizer thing, has anybody done any quantitative analysis how much organic fertilizer is required for this country for a season? And what sort of nutrition level is required? How to produce them, the machinery, manpower, supply chain, all these things, the cost. Did they take time to analyze all these things, quantify them before they decide? No, they didn't, because it was difficult to do all these things. What they did was they came out of into a public, in front of public, and explained very rosy story to everybody. And nobody could have said against, and anybody could have said against anything, could have been thrown away by everybody, the majority also, because this story was so pleasant and nice for a temporary pleasure. Without quantifying things, it is very, very risky to take a decision based on a rational concept. Think about solar energy. A lot of people are talking about solar energy, solar energy, solar energy. Sri Lanka has a lot of solar energy. We know it. Everybody knows it. And then they say, we can make cars, we can run factories, we can produce energy for houses, everything, everything. We don't need fossil fuel. Very fancy story. Why don't we do that? You have to quantify the thing to figure out how much energy can be harnessed from a solar panel, how much energy you need a day, how much energy you need to drive a car, what is the current density. It's not just the energy, the density that you need to drive a car, whether the solar panel has that current density, right? Without doing this science, quantifying things, right? People just talk about concepts and take decisions. This is very, very bad. They mislead the whole population and then pay the price after a little while. And today, any technically savvy person can go to the internet and download information about anything. Right? If I want to talk about potato cultivation, I know nothing about potato cultivation, but I can undertake to deliver a lecture about potato cultivation next week. I just need 1 week or even few days to become an expert in potato, because there's internet. I can go to the internet, download all these things, read a little bit, and all of a sudden I'm a potato expert. I talk about potatoes. And following week, if somebody tell me about, can you give a deliver lecture on what about COVID? I know a little bit of COVID. Everybody knows, but I'm not an expert. But I undertake. Okay, let's do that. I go to the internet, study about COVID. 5 days, I'm an expert. There are a lot of experts like that, temporary experts, they're very, very dangerous because they mislead the whole thing. Why? In a week, in few days, just by going to the internet, you cannot do the quantifying test. You can collect the information, you can collect the concepts, but you don't have time to experience it. You don't have time to quantify it. So whatever you talk about without quantifying things is most definitely a lie. It is not the reality. So this is how things happen in the society. So see the analogy between what we see, right, in political and social scenarios and what is happening, what has happened in the asteroid belt, right, of the solar system. It's quite amazing to see this correspondence. So the purpose of this lecture is just that. Just that. Try to bring your understanding from space or wherever and then reflect it onto something else and figure out the analogy and learn from each other, right? So that way you can actually short circuit your learning process and you can maximize the output. Right. So this is very interesting story. Now, there's another thing. Planetary embryos and small planetesimals of the asteroid belt might have thrown out by Jupiter, and some may have fallen on the Earth, bringing water here. Otherwise, water is too volatile to have been present at the Earth's formation. So this is another very interesting hypothesis, how we got water here on Earth. What is essential to many things, including life, and how we got it here. Our position, the fourth place, the third place from the sun, was too hot for water to present. Water is a volatile matter, right? But now we have a lot of water. And all the theories say we are too close to the sun, right? Not now, but at the beginning, when the earth was formed, it was hotter than today. Now it is cooled down to a certain extent. Now water can present here. But at the time of formation, there was no water because it was too hot for water to be stable. The water might have gotten here, not right from the beginning, but at a later time. It's obvious, right? Between then and now. So how can we explain that? How we got water if it was not there originally at the time of formation? You could have gotten it from the asteroid belt. Some asteroids coming towards the sun because the gravity of the sun, or maybe Jupiter is on the other side. Both Jupiter and sun, they pull the asteroid belts towards the sun. And while it was passing, there was earth in the way, and that asteroid fell on earth, bringing a lot of water, right? And that happened between then and now at some point, and at that time earth had been cooled to some level so that the water could present in a stable manner. So it's a very interesting story, right? Very interesting story. And there's a scientific explanation for every observation that we made. So I'm telling it again. If at least one of the observations, right, was not explained by the theory or by the hypothesis with a reasonable level of acceptance, then the hypothesis is in trouble. Okay. So hypothesis should be able to explain everything, every observation, like water here on Earth. Right? You can't say no. Hypothesis is not supposed to explain everything. No. Hypothesis is supposed to explain every observation, right? Because this hypothesis is about formation of the solar system. So everything is included, including the water, okay, on Earth. Now let's look at, by the way, so we have gone past 6. Shall we take about 5 to 10 minute break? Right? So I'll come back in 10 minutes. All right, we are back. So let's look at some of the specific information about Jupiter. Jupiter is the largest planet. So we need to be aware of some of the specific features there, right? So if you look at the Jupiter and the Sun, here you can see the Sun and the Jupiter, and you can put about 10 Jupiters from side to side, right, along the diameter. So it's like 1/10 of the Sun. And then here is the Jupiter and the Earth. Again, you can put about 10 Earths across the Jupiter. It's a really interesting scenario. This is again Earth and Moon, right? So in the solar system and the universe, you will continue to see these very nice ratios, right? So just as we move, you will see more of these. So it's like 1 to 10 between Sun and Jupiter, and again 1 to 10 between Jupiter and Earth. Again, sometimes it's just coincidence, right? There was no communication between Sun and the Jupiter and the Earth, and then they decide, okay, so you get to say 1/10 of my diameter, and then you get again 1/10 of that diameter. I don't think there was a communication like that, right? To make it like that. But I think there is physics behind everything, and the dynamics, the motions, the energy. Okay, if you put all these things together, right, you will see for a complex multi-body system to stay in a stable fashion, there should be some sort of uh, uh, ratios, right, between elements. So I'm not going to prove it by talk right now, right? You can learn it as we move. Time and time again, you can see these ratios popping up, and sometimes people take it too far and try to explain the mathematics, the number systems, etc., to the physical world, right? You have to be very careful when you do that. So there's another thing I want to tell you right here. Now, the whole solar system is a dynamic system. It's not a static thing, right? You have the sun, which is rotating, and sun is not a perfect sphere. It is kind of elongated in the equatorial plane, and the polar regions are not as long as the diameter on the equatorial plane, right? So these are changing things, and it emits a lot of energy. Sometimes it's very furious, right? And if you look at planets, they are moving. They are constantly changing their position, and they are going in elliptical orbits. They sometimes get a little bit closer than some other times, where they are a little bit farther away. And there are about 8 planets. Sometimes these planets align. Many planets like Jupiter, Saturn, Uranus, Neptune, on line, right? In a line, right, on one side of the sun. Then it creates lot of force in that direction, right? And some of the times they are scattered all over. Then the magnetic fields are actually like even out, balance out, cancel out. There are a lot of changes happening. And if you are just one member in the solar system, let's say you are, let's say Earth, for example. So we are pulled by the sun, we are pulled by the Jupiter, we are pulled by Saturn, Uranus, Neptune, we are pulled by everybody. And if you draw these gravitational forces, you will see again, you have to quantify. Okay, I'm telling this again. When you quantify, you can see, even though there are so many of these gravitational force lines, there's only couple of these lines which are significant from the line from the sun and the line from the Jupiter. And maybe you can consider the line from even Saturn and not from any other planet. So quantitatively, you remove the other things. So then you have to look at the three forces on the Earth. Ah, by the way, there is another close by member, the Moon. Moon is not very big, right? Like small, but it is very close to the Earth. So therefore, its gravitational force on the Earth can be significant as well. So these four lines, right? You draw, and on the Earth, you predict where the Earth is going to be next moment. And at that time, all the other objects have changed their positions, right? Then it's a different force field. So now you can imagine this constantly changing gravitational force field around us. Around us. Now, Earth is big and it's on a stable orbit. But if you think of an asteroid or a small particle, right, it's not as stable as the Earth. So there are force lines coming from everywhere. And look at a satellite around Jupiter, small satellite around Jupiter, right? Just to go around the planet Jupiter, it has to have a high speed, because if it doesn't fly that fast, it will spiral into the planet and fall, right? In order to go around the Jupiter, it needs to maintain this tangential speed, the orbital speed. Then only it can keep going without falling onto the planet or without escaping completely away from the planet. Now, the problem here is that if it is only Jupiter, that's okay. You can calculate the orbital velocity like you have done in A level, probably, right? It's a one-off calculation and it has to go maintain that speed. If it reduces the speed, it will fall into the planet, onto the planet. And if it speed it up, it will go out of the planet, spiral out and escape. So if it falls onto the planet, or if it completely escape the planet, spiral out, either way, it's not stable. You will not be able to see the asteroid for a long time, right? At some point in time, it will disappear. It's not there anymore. So that's what I try to explain, that they are not stable that way. Now think about, there are other planets around Saturn and also the sun on the other side. Now it's a very, very complicated gravitational force field because of the big multiple bodies around. Now, when you simulate this whole thing in a computer and you can run it accelerated process, millions of years in a couple of weeks maybe, you can see what's going to happen to that multi-body system, right? You cannot write down mathematical equations, differential equations, solve them, and you have the function of time. You substitute time equals million years, and then it tells you where the position of the planet. I don't think there's such thing. This is almost like chaotic. So you have to numerically solve the problems and run it. That's how they do that. That's why big computers are needed for these multi-body simulations. So when you do that, you figure out which of these planets or moons or asteroids or anything are actually stable in the long haul, or which of these objects that we see, like going around planets, moons, or asteroids, that we see as stable, how many of these things are going to be vanished or going to vanish at some point in the future, right? Because of the gravitational, the changes of the gravitational force field. Okay, every moment it's going to change. So if you think of a millennia period, it's hard for some of these small particles, objects to still stay, right, without being, uh, without falling into the planets or without being kicked out of the solar system altogether. Right? Having said that, if a, an asteroid or a moon or a satellite finds out if it is in a particular position and all the other big planets around it, right, they go around the sun, they go around each other in a cyclic manner. Maybe every 75 years it completes a cycle. So after that 75 years, you are repeating the same cycle. So you don't have a million-year indefinitely changing process. It's a 75-year change. So what this, from 75th, 6th year to 150th year is a repetition of the same thing. It's the repetition of the same thing. So if you are stable for the first 75 years, you're going to be stable for the next 75 years as well, and for any other 75-year period for that matter. Understand? So all these objects that you see out there, right, if at all possible, if they have some sort of time scale within which, right, they are stable, and the time scale means the cyclic time scale, then they are going to be stable for a long period of time. So that is why you see most of these planetary bodies, they show some sort of cyclic thing, some ratio 1 to 10, 1 to 5, 1 to 4, something like that. So which means after 4 cycles, 5 cycles, 6 cycles, they gonna repeat the same thing again, right? So you only need to be stable within that, however, whatever number of cycles, right? After that is more of the same again, okay? So therefore, you are not going to be unstable. So if you see some sort of cyclic thing in the space, in the planets, in the solar system, they have achieved this dynamic equilibrium. So they are going to be there for a long period of time. If you don't see that kind of cyclic thing, we don't know what's going to happen to them, right? So that's why we can see a lot of cyclic things, right, in the solar system. So don't get like astonished or surprised by that when you see some sort of cyclic ratio kind of things, right? Because of that ratio, they are there. Okay, somehow or the other, they have achieved the cyclic thing, right? And if you drop a ball from a height, it will fall. So like that, if an object in the space is not stable, right, it will go through a certain trajectory until it finds some sort of stable motion. And if it is cyclic thing, it will come back to the same position over and over again. And when we observe, we can see these stable objects because They have reached the cyclic equilibrium. So there's nothing to wonder, nothing to be surprised too much when you see these ratios. Like, for example, do you know that when you look at the moon, we always see the same side of the moon? Have you ever wondered that? Have you ever wondered that? Because moon is not a disk, no? It's a three-dimensional body. It has a surface. When you see it, right? Why are we seeing the same side over and over again? We never see the other side of the moon. So if it is a solid three-dimensional body, there are two sides, no, right? Why don't we see the other side? So can somebody explain that? Have you ever wondered about that? Oh, it's not your problem. I don't care, right? So can somebody answer that question, please? If you get a photograph of the moon today, tomorrow, day after, one whole year, you will see the same side, same structures. Have you ever wondered? Because this is not a plane. No? Moon is not a plane. Okay, it's not a 2D plane like a photograph. It's a solid three-dimensional body, right? If you look at the Earth, you have seen different photographs where in some photos you can see one side, some other photos you can see something else, the Asia, the Australia, America. It's like that, three-dimensional, right? Photos are different. But if you look at the photos of the moon, taken from the Earth, of course, right? Same features, same photo. Why? Any answer? My God, no answers. Unbelievable. This is simple, very simple question. Please answer.
Because rotation of the moon around the earth and its rotation about its own axis synchronizes.
Yes, not the synchronized, it's same period, okay?
Yeah.
Yeah, so yeah, you can say synchronized. It takes about 27 and a quarter days for the moon to go around the earth, right? And then in the same time, 27 and one quarter days, it completes one spin around it. Who would believe if you say that? If you don't show the photographs and you tell to somebody who has never seen the moon, right? So in this course, we ask these questions. Sometimes the questions like very silly, nonsense, but we don't care. We have to ask these questions. If there's somebody here on the earth who has never seen the moon, and you explain to him there is something called moon, and it's going around the earth 27 and one quarter days, and it also spins around its own axis 20 exactly 27 and a half quarter days. Who would believe you? They will say, my God, you're telling nonsense. How can that happen? This kind of synchronism, unbelievable, right? Unless somebody created it. And of course, no offense to any religion, any belief. I don't believe there's a creator and this all happen naturally. Unless you call the creator is the nature. I don't believe, I have no reason to believe it was purposefully created. Okay. But if any one of you want to believe it that way, I have no objection. Please do so. Right? But individually, you have to think it yourself, right? This is perfect synchronism. Nobody would believe that kind of thing, right? But again, if you look at the physics side of that, I can explain it in a different way. Uh, It's actually a moment in time that we see Earth and Moon, this synchronism, right? It was not like this a million years ago, and it will not be like this million years later. I will explain that in future slides, right? Is changing. Right at this moment, we see as a synchronism. And the second thing, I just explained the synchronized, or in a different way, I call it cyclic, right? Cyclic equilibrium. If a system is stable, right, it lasts for a long time. If it is not stable, it will change and it will disappear. Okay. Now, if you have a very, 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 very old system, if you have very, very old system like solar system today, whatever you see is actually the stable systems. Let's say your initial system, let's say your initial solar system had 1,000 objects, and over the course of last 4 billion years, maybe, or so, some of these unstable things have gone here and there, fallen onto other planets, because they were all unstable. They were not able to get into a synchronism. So if you think of 1,000,000 objects, now we see only 10 or 8, right? You think how many was there initially? Million is a very small number. It's billions of objects. And almost all of them are unable to find its own equilibrium. So they were fallen to other objects, they were thrown out of the solar system. Some actually went on and fall on the sun. Most of the objects were not fortunate. So now what we see is not a general objects. All of these things are like very lucky objects, right? Extremely, extraordinarily lucky objects that you see here. Now think about yourself, those who come tomorrow to Earth. Is this the general population of students? No. You have been very lucky to be selected tomorrow to Earth in the first place, right? There were about 90% out there who couldn't make it. Now, when we look at you, right, you are here because you were extremely lucky in a way, I would say, or extremely talented, either way, both, right? So, solar system is also like that today. Whatever we see, the objects and all, they were 1 out of 1 billion, right? That was able to somehow find the equilibrium, the synchronism, the cyclic motion. Okay? Only 1 out of 1 billion or few billion, maybe kind of random, right? Is not a deliberate thing, it's a random thing. Are visible today, are there in their stable orbit. And all the others, they couldn't make it. Simple as that. So therefore, there's no wonder we are not seeing a general population. We are not seeing a general population. If you look at your exam results and everything, is it a general distribution? No, not at all. Not at all. Now, if you think of, I'm trying to explain you something very fundamental, but something you find it difficult to understand. Let's say if we have 1,000 students sitting for an exam, if we draw the histogram of their subjects, right, average, we get a normal distribution. Everybody knows about it, right? Normal distribution. And probably we would get a very normal distribution. Average is like 50, 55. And we have fewer people in 80 plus range, and also fewer numbers below 20 marks, right? And majority in the middle. So that is the general population. Now, if we look at the marks distribution at the university or different faculties, departments, etc., we don't have a normal distribution. We don't have a normal distribution. Because if you look at the average, sometimes average goes to about 70. And there are no people, probably maybe one or two, below 40. So everybody scores beyond 40. So is it a normal distribution? No, it is not. We are not seeing the normal distribution. Okay, then if we just look at the distribution and say this is not normal, it's not correct. We are not actually dealing with a normal set of people, students. This is an abnormal distribution, a school distribution. Do not expect the students' marks to be normally distributed. Maybe you don't like it because you want to have everything normally distributed. Unfortunately, sorry to say, here it doesn't happen. Okay, at the universities. So I'm referring to any university for that matter. Because when you have a specially selected set of people, then right at that moment, you don't have the normal distribution, right? So you never expect anything to be normally distributed. Here also the same. The solar system, if you look at today, right, you see very, very special features because this is not the normal distribution again, right? After billions of years, all the anomalies have been removed from the system. It's a cleansed, clean system. And when you look at it today, you will see a very, very special case. Okay, very, very special case. And this all happened through the evolution of billions and billions of years. Therefore, there is no reason for a creator to create it in that way. It was not created this way billions of years ago. It was a very different situation, very chaotic. Particles are moving here and there. It was not having any order at the beginning. Highly disturbed, disorganized system. Just a big gas cloud, nothing but a gas cloud. Okay, there was no order there. It's only now we can see some sort of order through the evolution. Okay, so if you understand that the whole process, the dynamics, the quantification and all that, there's no reason to believe anything beyond our normal senses, physics, right? It can be explained. Right. Any questions so far? Sometimes I take too long for a certain thing, but it is the whole purpose of this course, right? Whole purpose of this course is not to cover too many, but cover something um, to a depth, and complete understanding. That is the purpose. Now, what you see here is very interesting thing. You can see Jupiter here, right in the middle. And this animated GIF, you can see 3 satellites, natural satellites of Jupiter. Jupiter right in the middle. The first one is Io. Second one is Europa. Third one is Ganymede. Okay. If you look at the Europa, it goes around Jupiter. Let's take the period of revolution, let's say any time, any t, right? And if you look at Europa, it goes around, revolve around planet in 2t time. It takes twice as long as Io. And then if you look at Ganymede, it takes 4 times. It takes 4 times. Now again, when somebody shows this to someone, they would say, "My God, what is this? This is absurd. How can this be synchronized like that?" Did somebody create it that way? Or was it like that forever, right from the beginning? And will it be like this after million years? Probably not. What we see is a moment of time, and today it's like this. It was not like this millions and millions of years ago, and it will not be like this in the future also. Again, I have to tell you the same thing. If you look at the cycles, right? The first cycle of Io is subjected to different varying magnetic field, gravitational fields. Second cycle, it also feels different gravitational fields. Third cycle, yes. Fourth cycle, yes. Fifth cycle, no. The fifth cycle of Io is similar to the first cycle of Io. Can you understand that? So after 4 cycles of Io, things will start over again. Things will start over again. So if Io can somehow hold it for the first 4 cycles, somehow, without falling onto the Jupiter or without being completely kicked out of the system, if Io can stay there for 4 cycles, somehow hold it, then Io can continue to hold its position indefinitely. Because what follows after 4 is the same thing that was there in the first 4 cycles. And you can tell the same thing about Europa also. Did you get my point? Yes or no? Are you there? Are you there, guys?
Yes, sir.
Yes, sir.
Yeah, so did you get my point? If Io can somehow hold on to its position, its motions, dynamics in 4 cycles, right? Then Io will continue to be stable indefinitely. Did you get that point? So I think yes, okay. So what we see today is very special things in the solar system, as I explained earlier, right? Because Io, Europa, and Ganymede, together with Jupiter, right? Because they were able to meet this cyclic stability, right? They are stable today. So they are going around Jupiter in a stable orbit, right? And they are stable for a long period of time. Okay. There was no reason to surprise Why it is like that? Because of the evolution, they have eventually got into this dynamic stability. And also you can see a lot more of the same nature. Jupiter and Saturn underwent orbital changes and eventually reached 2.5 orbital resonance. 2 rounds around the Sun for Jupiter, um, uh, Saturn, and 5 times around the Sun for Jupiter. So Jupiter goes 5 times and Saturn goes 2 times. So then the 2 planets are stable after that. So 5 cycles of Jupiter. So Jupiter has 5 cycles around the Sun to stay stable, right? And what follows next is the same thing within what happened within that first 5 cycles. So therefore, it's going to be stable. So therefore, we do not have to worry about every second, every minute of every planet to check whether they are stable or not. If they have already reached this kind of cyclic stability, we only need to worry about within the cycle. We have to simulate and figure out whether they are stable within the cycle. Of course, they are. And then all the dynamics that follows after that is the same dynamics that takes place in the first cycle. Okay. So there's a lot more like that. So Jupiter and Saturn caused Neptune to move outward and also ejected planetesimals towards far reaches of the solar system. So if anything that was not able to reach this kind of cyclic equilibrium wouldn't have um, uh, ceased to exist by now, right? Either have been fallen onto the planets, thrown out of the solar system altogether. So they're all unfortunate members, very unlucky members of the solar system. And what we see today is a very special set of remaining objects, and they are in very stable cyclic uh, uh, dynamic equilibrium. Okay, so I want to stop today at that point, slide number 21. Any questions, please?